Subscribe to the channel and like the video. Somewhere, in the deepest stretches of the cosmos, far beyond the reach of even our most powerful telescopes, a silent, ancient giant waits in the shadows. Its surface blazes with unimaginable heat, its heart churns with nuclear fury, and its mass bends the very fabric of space. For millions of years, it has been stable, burning its fuel in a delicate cosmic balance. But one day, that balance will shatter. In a fraction of a second, the calm will give way to chaos, a cosmic detonation so powerful that it will outshine entire galaxies, briefly becoming the brightest object in the observable universe. And here's the most staggering part: this is not science fiction. This is real. It has happened before. It will happen again. And when it does, it will unleash the most violent, most energetic, most awe-inspiring event known to humankind. There's an explosion so powerful it outshines entire galaxies. And it's real. Now, pause for a moment and try to wrap your mind around what that means. An entire galaxy contains hundreds of billions of stars, each one a blazing furnace of nuclear fusion. Imagine all of that light, billions of suns, combined into a single brilliant glow. Now imagine a single point in space suddenly becoming brighter than all of them put together. The scale is so massive, so beyond human comprehension, that we can only describe it in metaphors and comparisons. And yet, nature creates such explosions without hesitation, scattering energy across the universe like it's nothing more than an afterthought. When this event occurs, its light can travel for billions of years and still be bright enough for us to see from Earth. Its energy can rival the combined output of every single star in every single galaxy we can observe. And even though it lasts mere seconds to minutes, the aftershocks echo through the cosmos for millions, sometimes billions, of years. In those brief moments, the universe seems to hold its breath, as if acknowledging the birth of something monumental, and the death of something equally so. These explosions aren't just bigger supernovae. They are in a class entirely their own, a rare and terrifying cosmic phenomenon that redefines what we think power means. They are the kings of destruction, the architects of creation, and possibly the reason planets like ours even exist. And yet, they are not fantasy. They are a cold, scientific fact. We've observed them. We've measured them. We've seen their fingerprints in the distant universe. And in studying them, we've not only discovered their ferocity but also their role in shaping the very matter that makes up our bodies, our planet, and our civilization. This is not just a story about explosions. This is a story about the most powerful thing the universe has ever shown us, and what it means for life itself. What could possibly unleash such unimaginable energy? It's the kind of question that makes even seasoned scientists pause, because when you truly think about the scale we're talking about, you start to realize how utterly alien these events are to human experience. Every explosion we've ever created on Earth, every volcanic eruption, every nuclear detonation, every asteroid impact, shrinks into insignificance compared to this. Even the might of the Sun, our own star, which produces enough energy every second to power all of human civilization for millions of years, is nothing more than a cosmic candle flickering in a vast and stormy night. If you stood at a safe distance, which, for the record, would have to be millions of light-years away, and looked upon one of these events, the light would pierce your eyes like the midday sun, even though it had traveled through the vacuum of space. For an incomprehensible length of time. Your brain would struggle to reconcile the fact that what you were seeing wasn't just a star exploding. It was a cataclysm so vast it would make the word explosion feel too small, too tame. And this is where the mystery deepens. Because when astronomers first detected the signals from these titanic bursts of energy, strange, fleeting pulses of high-energy light, they didn't know what they were. At first, these cosmic beacons were nothing but data points, puzzling flashes recorded by satellites designed to look for nuclear tests here on Earth. The readings were bizarre, short-lived, incredibly intense bursts of gamma radiation coming from random points in the sky, with no clear pattern or source. They were too powerful to come from anything familiar, too brief to be a steady source like a quasar, and too common to be dismissed as an anomaly. So the question loomed large: what could possibly generate that much energy, in that short a time, and from so far away? Was it colliding stars? Was it the death of the most massive stars in the cosmos? Was it something stranger, perhaps even a completely unknown type of physics in action? These weren't idle questions. The stakes were high, because the answers might reveal not only the cause of these events, but also deep truths about the structure and fate of the universe itself. For decades, scientists chased this puzzle. They built better detectors, positioned satellites above Earth's atmosphere to catch the faintest glimmers, and began to notice something extraordinary. Many of these bursts were accompanied by visible light events, supernovae, but of a kind far beyond the ordinary. This was the first clue that these explosions weren't just random gamma-ray flashes. They were tied to the deaths of stars so massive, so extreme, that their very end became a weapon of energy unlike anything else we'd seen. But before those connections were made, these bursts sat in the annals of astronomy like unsolved crimes, enigmatic, powerful, and slightly terrifying. Imagine looking up at the night sky, knowing that somewhere out there, something has gone off with the force to wipe out entire solar systems, and yet you have no idea what it is. You don't know how far away it happened. You don't know how often it occurs. You don't even know if one could be aimed at us right now. That's the kind of unease this mystery carried with it. It's worth remembering that in space, distance doesn't mean safety. The radiation from some of these events could be dangerous even from thousands of light years away. That knowledge added a layer of urgency to the mystery, because if you don't know what's causing it, you also don't know how to predict it or prepare for it. And so, the search intensified. Year after year, the evidence built up. Patterns emerged. Some of these bursts lasted just milliseconds, others several minutes, but the long ones, those stretching beyond 2 seconds, often seemed to be linked to a rare, ferocious type of stellar death. These weren't just any stars. They were titans, 30, 50, even 100 times more massive than the Sun. And when they died, they didn't just collapse. They detonated with the fury of a billion nuclear bombs going off at once. In time, the name was given, hypernova, a word that carries within it both its origin and its absurd scale. Hyper for its sheer excess, nova for its connection to the supernovae we'd known before, but make no mistake, this is no mere supernova. This is the heavyweight champion of the universe's arsenal of destruction. But before the term became common, the mystery had already pushed astronomy into new territory. It forced us to look at the life cycles of massive stars with fresh eyes, to think about the mechanics of stellar collapse in ways that tested our understanding of physics at the extremes. How do you even describe a process that converts the core of a massive star into a black hole, while simultaneously launching jets of matter and radiation at nearly the speed of light? How do you model something that can release more energy in a few seconds than the Sun will emit over its entire 10 billion year lifetime? The mystery, when it first came to light, was both a scientific puzzle and an existential reminder of our smallness. We could only watch and wonder, piecing together the clues like detectives at a crime scene, knowing that somewhere in those numbers and flashes of light lay the key to understanding one of the greatest forces the universe had to offer. It was a question that demanded an answer, because it touched on so many others. How do stars die? How do black holes form? Where did the gold in our jewelry, the uranium in our reactors, and the platinum in our electronics come from? Could these cosmic events have influenced the development, or destruction, of life across the universe? And in asking that central question, what could unleash such unimaginable energy? We set ourselves on a path that would lead to one of the most astonishing revelations in modern astronomy. The hypernova, the universe's most powerful known explosion. It's called a hypernova, the universe's most powerful known explosion. The name alone feels almost inadequate, because when we talk about a hypernova, we are talking about an event that sits at the very edge of what's physically possible. This is not just the death of a star. It's the universe wielding its most devastating weapon. Imagine the titanic forces of a supernova and then multiply them, not by 2 or 3, but sometimes by more than 10. The result is a blast so luminous it can briefly rival the combined light of every single star in an entire galaxy. For a long time, astronomers thought supernovae were the pinnacle of stellar violence. They were already dramatic enough, immense explosions marking the deaths of stars many times the size of our Sun, scattering the elements needed for life across space. But then came data that didn't fit. Observations showed certain stellar deaths producing bursts of energy that eclipsed even the most energetic supernovae. These weren't subtle differences, these were orders of magnitude beyond what the models predicted. That's when the term hypernova came into play, a label for an event so rare, so extreme, that it demanded its own classification. In essence, A hypernova is a kind of supernova, but one pushed to the absolute limits of stellar collapse. In this cosmic drama, the dying star doesn't just blow off its outer layers. Its very core undergoes a catastrophic implosion, often forming a black hole in the process. But before that black hole swallows everything around it, something astonishing happens. Twin jets of energy and matter blast out along the star's rotational axis at speeds approaching the speed of light. These jets punch through the star's outer layers, releasing an almost inconceivable amount of energy into space. The power output of such an event is staggering. In a matter of seconds, a hypernova can radiate more energy than the sun will produce over its entire 10 billion-year lifespan. Think about that. All of Earth's history, from its fiery birth to the present day, powered by the sun's constant fusion furnace, and a hypernova matches or exceeds that entire sum in less time than it takes to read this sentence. It's not just powerful, it's violent, sudden, and transformative. These explosions are so intense that they often produce another phenomenon entirely: gamma-ray bursts. For observers lucky, or unlucky, enough to be aligned with the jets, the gamma radiation can be so bright that it saturates detectors across vast distances. If one of these bursts were to happen within a few thousand light-years and aim directly at Earth, it could strip away our planet's ozone layer and potentially trigger a mass extinction. Thankfully, hypernovae are exceedingly rare, and the odds of one going off close enough to threaten us are vanishingly small. But the possibility is not zero, and that mere fact is a sobering reminder of how fragile life can be in a universe that contains such power. Still, for all their destructive potential, hypernovae are also creators. The unimaginable temperatures and pressures inside these explosions forge some of the heaviest elements in the periodic table: gold, platinum, uranium, flinging them into space to seed future generations of stars and planets. Without them, the universe as we know it, rich in heavy elements and complex chemistry, simply wouldn't exist. So when we name it hypernova, it's not just an astronomical term. It's a recognition that we found the ultimate in cosmic fireworks, the event that outshines galaxies, that bends the rules of energy output to their breaking point, and that forever reshapes the space around it. It's the ultimate answer to that earlier question: what could unleash such unimaginable energy? This is it. This is the cosmos at full throttle. A hypernova is, at its core, an extremely energetic type of supernova. So much stronger, brighter, and more violent than the normal variety that it exists almost in a different category of stellar death altogether. To understand it, we first have to take a step back and look at what a normal supernova is, because even those are among the most powerful events in the universe. A supernova happens when a massive star, typically between 8 and maybe 20 or 25 times the mass of our Sun, reaches the end of its life. The nuclear fuel that powers it runs out, fusion stops, and gravity, which the star has been holding at bay for millions of years, wins. The star's core collapses in a fraction of a second, triggering an immense shockwave that blows the outer layers into space. For a short time, the supernova can shine brighter than the entire galaxy it lives in. Now take that process and dial up the intensity, not by a little, but by a staggering margin. A hypernova occurs when a star at least 30 times the Sun's mass, and sometimes much larger, dies in an even more catastrophic collapse. The physics that follows is more extreme in every possible way. The core falls in on itself so violently that it often forms a black hole instead of a neutron star. Enormous amounts of gravitational potential energy are released, and in some cases, rotational forces and magnetic fields channel this energy into narrow, high-speed jets that rip through the star's outer layers. In raw numbers, the difference is jaw-dropping. A typical core collapse supernova might release around 10 44 joules of energy in visible light, with the rest in kinetic energy and neutrinos. A hypernova can release 10 times that amount, and sometimes more. To put that into perspective, 1 joule is the energy needed to lift an apple a meter off the ground. Now imagine multiplying that by a 1 followed by 45 zeros, and then multiplying it again by 10. That's the kind of power we're talking about. Hypernovae also differ in the way they shine. Their luminosity can reach absolute magnitudes of around -21 to -23, which means they can be billions of times brighter than our Sun. 4 days or weeks, they can outshine the rest of their host galaxy. Astronomers observing them from across billions of light-years can still detect their light, faintly but clearly, even after it has been traveling through the void for most of the history of the universe. One reason they're so much more energetic is the sheer amount of material involved. Massive stars have far more mass to collapse and eject than smaller ones, and the gravitational energy released when that much mass falls inward is exponentially greater. Add in rapid rotation, intense magnetic fields, and the possibility of relativistic jets, and you have a recipe for the most violent stellar death imaginable. Another key point is the role of gamma-ray bursts. Many of the most powerful hypernovae we've observed are associated with long-duration gamma-ray bursts lasting more than 2 seconds, often tens of seconds. The gamma rays we detect from these bursts are just a fraction of the total energy released, but they are the most intense electromagnetic radiation the universe produces naturally. A regular supernova might not produce such a burst at all, but in a hypernova, the combination of black hole formation and jet production makes them much more likely. It's important to note that not every massive star collapse produces a hypernova. Many still end their lives as more ordinary supernovae. The exact conditions needed, rotation rate, magnetic field strength, core structure, are still areas of active research. But when those conditions align, the result is unmistakable. The star's death becomes not just a bright flare in the night sky, but a cosmic event visible from the other side of the universe. So, if a normal supernova is a kind of celestial citywide fireworks show, a hypernova is the equivalent of detonating every nuclear warhead ever built, in every country, all at once, and then multiplying that by billions. It is the biggest, loudest, brightest way a single star can say goodbye. Hypernovae are born from the most massive stars in the universe, true cosmic heavyweights whose size and energy output defy everyday imagination. These are not the modest, middle-aged stars like our Sun that can live in quiet stability for billions of years. No, these giants live fast and die young, burning through their nuclear fuel at an astonishing rate, their lifespans measured not in billions, but in mere millions of years. And their size is key to why they end their lives in such an extraordinary way. For a hypernova to occur, the progenitor star must usually be at least 30 times the mass of the Sun, though some candidates are much larger. 50, 80, even over 100 solar masses in extreme cases. This sheer mass fundamentally changes the way the star lives and dies. More mass means more gravity, more pressure in the core, and therefore higher temperatures. These conditions drive nuclear fusion at a furious pace, allowing the star to fuse heavier and heavier elements far more quickly than a smaller star could manage. While our Sun takes billions of years to burn through its hydrogen, these giants exhaust their fuel in a fraction of that time. Such stars often belong to a class called Wolf-Rayet stars. These are stripped-down, luminous behemoths, often having lost their outer hydrogen layers due to intense stellar winds. They shine millions of times brighter than the Sun, their surface temperatures reaching tens of thousands of degrees. The energy they pour into space every second is staggering, and it's all fueled by a core that is steadily fusing its way up the periodic table, building layers of helium, carbon, oxygen, and heavier elements like an onion. This rapid fusion comes at a terrible cost. With so much mass bearing down on the core, the star is constantly fighting a losing battle against gravity. As fusion progresses and heavier elements form, the reactions produce less and less energy relative to the gravitational pressure. Eventually, the star reaches iron in its core, and iron is the end of the line for fusion in normal stellar physics. Fusing iron actually consumes energy rather than releasing it, so the star's nuclear engine effectively stalls. In a smaller massive star, say, around 10 or 15 times the Sun's mass, this collapse can trigger an ordinary core collapse supernova, leaving behind a neutron star. But for a star with 30 solar masses or more, the situation is much more violent. The enormous gravitational potential energy, combined with the possibility of rapid rotation and powerful magnetic fields, doesn't just cause the core to collapse, it funnels the collapse into conditions extreme enough to form a black hole almost instantly. What makes these massive stars so prone to hypernovae is the sheer scale of the collapse. The larger the star, the more gravitational energy is released when its core falls inward. In some cases, the star's rotation and magnetic fields direct part of this energy into focused, high-speed jets along its poles. These jets, moving at nearly the speed of light, plow through the star's outer layers, blasting them apart and releasing energy far greater than a typical supernova. The result, a hypernova. Interestingly, such massive stars don't always live in isolation. Some are in binary systems, where their mass and angular momentum can be influenced by a companion star. These interactions can strip away outer layers, increase rotation speeds, and make the conditions for a hypernova more likely. But whether isolated or in a pair, their massive size ensures one thing: when they die, they don't just fade away. They go out in a spectacular blaze that can be seen across the universe. There's also a cosmic irony here. The most massive stars, which seem so dominant and enduring when you see them in the night sky, are actually the shortest lived. They blaze with such intensity that they burn themselves out in only a few million years, a blink of an eye in cosmic terms. And when that time is up, their death is anything but quiet. These stars are the universe's drama queens, enormous, bright, unstable, and destined for an ending so over the top that it makes every other kind of stellar death look modest. Without them, we would have no hypernovae. And without hypernovae, the universe itself would be poorer, less luminous, less dramatic, and perhaps even less capable of producing the complex chemistry needed for life. The collapse process is the violent heart of the hypernova story, a sequence of events that unfolds in a matter of seconds, yet involves energies so vast they could rewrite the destiny of entire regions of space. To the star, it is the end of everything it has been for millions of years. To the universe, it is just another step in the endless cycle of creation and destruction. By the time a massive star reaches the end of its life, it has burned through layer after layer of nuclear fuel. In its last days, or rather, its last minutes, the core is a densely packed sphere of iron, surrounded by concentric shells where lighter elements are still fusing. As we know, iron fusion is a dead end. Instead of releasing energy, it consumes it, so the moment the core is dominated by iron, the star's internal furnace sputters and goes cold. Without that outward radiation pressure to counteract gravity, the balance is broken. Gravity takes over with catastrophic speed. The core begins to collapse inward, accelerating under its own enormous weight. Imagine the mass of 30 suns worth of material, compressed to the size of a planet, then a moon, then a city, then smaller still, shrinking faster than you can blink. In less than a second, the core's density rises to levels that rival the densest objects in the universe. Temperatures soar to billions of degrees. At this point, two fates are possible, depending on the star's mass and conditions. If the core is massive but not overwhelmingly so, the collapse will stop when nuclear forces and neutron degeneracy pressure push back, creating a neutron star, a sphere only about 20 kilometers across but with a mass greater than the Sun. But in the case of a hypernova progenitor, the core's mass usually exceeds even that limit. Neutron degeneracy pressure, the quantum mechanical effect that can support a neutron star, simply can't hold up under the crushing gravity. The collapse doesn't stop. When that happens, the core keeps falling inward until it passes the event horizon, the point of no return. A black hole is born. Around it, a swirling maelstrom of superheated plasma forms as the infalling stellar material smashes into itself, releasing vast amounts of gravitational energy. Magnetic fields, wound tighter and tighter by the rotation of the core, funnel some of this energy into two narrow, oppositely directed jets that shoot out along the star's rotational axis. These jets are among the most extreme phenomena in the cosmos. They're made of matter accelerated to nearly the speed of light, accompanied by an intense outpouring of high-energy radiation. As they tear through the collapsing star's outer layers, they heat and blast the material outward, unleashing the full brilliance of the hypernova. This process is so rapid and so violent that, from start to finish, the star's transformation from a massive, stable sphere into a black hole or neutron star happens in mere seconds. In a more ordinary supernova, the shockwave from the core bounce, caused by the sudden halt in the collapse when the neutron star forms, pushes the star's outer layers into space. In a hypernova, the energy budget is much larger, and the jets themselves play a key role in punching through the star's envelope. Once they break free into space, they can extend for light years, visible as beams of gamma rays to distant observers. And then, almost as suddenly as it began, the collapse is over. The core is gone, replaced by a gravitational singularity or an ultra-dense neutron star. Around it, the debris from the star expands outward at a significant fraction of light speed, carrying the fingerprints of the elements created in the blast. For the black hole, the hypernova is only the beginning. It may continue to feed on the surrounding matter for years or centuries, growing in mass and influence. This entire process is a paradox. In just a few seconds, the star is both destroyed and transformed. Its familiar surface is gone forever, But in its place is a new, more compact, and far stranger object, a neutron star that spins hundreds of times a second, or a black hole that swallows light itself. And all around it, the aftermath of the explosion will reshape the surrounding space for millions of years to come. The moment the hypernova's core collapses and the black hole or neutron star forms, the star's death enters its most spectacular phase, the release of energy on a scale almost beyond numbers. This is where the universe shows its full hand, where raw gravitational fury is converted into a blinding, unstoppable outpouring of light, heat, and motion. The key players here are the relativistic jets, narrow streams of matter and radiation hurled into the cosmos at speeds so close to that of light that the difference becomes almost academic. To understand why this happens, picture the core of the star just after collapse. If it's a black hole, the material that doesn't fall directly in begins to spiral around it in an accretion disk, a glowing, churning whirlpool of plasma hotter than anything we could recreate on Earth. The temperatures reach billions of degrees, and the magnetic fields become unimaginably strong, twisted tighter and tighter by the rotation of the disk. These magnetic fields act like cosmic launch rails, channeling some of the disk's matter along the black hole's rotational axis and flinging it outward with astonishing efficiency. The result is a pair of oppositely directed jets, each one only a few degrees wide but containing a staggering fraction of the explosion's total energy. These jets are not gentle. They plow through what's left of the star's outer layers at nearly the speed of light, compressing and heating them until they burst outward into space. The collision between the jets and the surrounding material produces shockwaves and an outpouring of high-energy radiation, X-rays and gamma rays that can be detected across billions of light-years. The energy involved is staggering to the point of absurdity. At peak power, the jets of a hypernova can emit more energy in a single second than our Sun will produce in its entire 10 billion-year lifetime. That's not hyperbole, it's a direct calculation from observational data. For a brief moment, a hypernova's jets can outshine every star in every galaxy within view. And because the jets are so tightly focused, their apparent brightness to an observer aligned with them is even greater, a phenomenon known as relativistic beaming. This is why gamma-ray bursts linked to hypernovae are some of the brightest events ever recorded in the universe. If one of these jets were to point directly at Earth from within a few thousand light-years, the consequences would be devastating. A flash of gamma rays strong enough to strip away the ozone layer and flood the surface with lethal radiation. But from a safe distance, the jets are not a threat, they are a marvel. They act as messengers, carrying information about the hypernova across the cosmos. By studying the gamma-ray and X-ray signals from these jets, astronomers can infer the details of the explosion, the speed of the jets, the mass of the star, the structure of the collapsing core. They can even measure tiny variations in brightness caused by interactions between the jets and surrounding material, which tells us about the environment the star lived in before it died. Once the jets break free from the star's envelope, they expand into interstellar space, pushing a shock front ahead of them. This shock accelerates particles to extreme energies, creating afterglows that can persist for days or weeks in visible and radio wavelengths. These afterglows are often the first clue that a gamma-ray burst, and therefore a hypernova, has occurred. It's important to realize that these jets are not side effects, they are central to the hypernova's incredible energy release. Without them, much of the energy from the collapse would remain trapped inside the star, and the explosion would be far less luminous to distant observers. In a sense, the jets are the hypernova's way of shouting its existence across the universe. They are also nature's most efficient accelerators. The fastest particles in the jets approach the speed of light so closely that their kinetic energies dwarf anything achievable in our most advanced particle colliders. It's entirely possible that hypernova jets are one of the main sources of the highest energy cosmic rays that strike Earth, particles so energetic they defy easy explanation. When you think about it, the jets are the purest expression of the hypernovas. Violence, tightly focused beams of matter and light, launched from the edge of a newborn black hole, punching their way through the remains of a dying star and carrying its final message outward at nearly the ultimate speed limit of the universe. They are the reason we can witness these events from across the gulf of time and space, and they are the most dramatic reminder that when the universe decides to go big, it does so in ways that leave even our wildest human imaginings far behind. If a supernova is a sitter-leveling detonation in the cosmic sense, then a hypernova is the equivalent of detonating every weapon, every fuel source, every ounce of stored energy in that city, then multiplying it until the numbers stop making sense. Both are the deaths of massive stars. Both are spectacular beyond anything humanity can create. But in terms of sheer energy, a hypernova dwarfs a regular supernova so completely that calling them by similar names almost feels misleading. Let's start with the basics. A typical core collapse supernova, already one of the most powerful known natural events, releases around 10 carat 44 joules of energy in visible light, and roughly 10 carat 46 joules in total energy output when you include neutrinos and kinetic energy. That's enough to briefly outshine an entire galaxy and hurl stellar material into space at thousands of kilometers per second. If one occurred within a few tens of light years of Earth, it could cause serious biological damage to our planet just from the increased radiation. Now take a hypernova. In total energy, these monsters can unleash 10 carat 47 joules or more, 10 times the energy of a typical supernova, sometimes even exceeding it by a factor of 50 in certain cases. That's the equivalent of turning the sun's entire lifetime energy budget into a flash that lasts mere seconds or minutes. The difference is like comparing a matchstick to a thermonuclear bomb, except here, the bomb is on a scale so vast we struggle to put it into any human frame of reference. One reason for this enormous leap in energy is the role of the relativistic jets. In a regular supernova, the explosion is more or less spherical. The shockwave spreads outward evenly in all directions. In a hypernova, much of the energy is concentrated into narrow beams, making the energy density in those directions vastly greater. For observers lined up with one of these jets, the apparent brightness can be thousands of times higher than even the most luminous supernova. Another difference is the speed of the ejected material. While a typical supernova might throw its debris into space at a few percent of the speed of light, a hypernova's jets accelerate matter to nearly the speed of light, more than 99% of it, in some cases. That's a relativistic regime where the normal rules of intuition break down. These speeds make the shocks generated by the hypernova far more energetic, which in turn makes the event brighter and more destructive. The light curves, the graphs of brightness over time, also differ dramatically. A regular supernova rises to peak brightness in a few days and fades over weeks or months. A hypernova's gamma-ray burst component is over in seconds to minutes, but its afterglow can be detected for weeks, with the visible light often starting at much higher luminosity than in ordinary supernovae. This initial brightness spike is so intense that hypernovae can be detected from billions of light-years away, whereas most supernovae are only visible within a much smaller cosmic neighborhood. If we could somehow set a regular supernova and a hypernova side by side in the night sky, ignoring for a moment the inconvenient fact that the radiation would kill us, the difference would be obvious. The hypernova would blaze so brightly that it would cast shadows at night on Earth, even from millions of light-years away. The regular supernova would still be brilliant, but next to a hypernova, it would seem almost muted. Perhaps the most telling difference is in their cosmic roles. Both types of explosions create and disperse heavy elements, but hypernovae are thought to be the primary source for some of the rarest and heaviest elements in the universe, like gold and platinum, because their extreme energies and conditions allow nuclear reactions that don't happen as efficiently in normal supernovae. They are also far more likely to leave behind black holes rather than neutron stars, meaning their endings are more extreme not just in light, but in the final objects they produce. In other words, while a supernova is already a universe-shaking event, a hypernova is the next level, the top rung on the ladder of known stellar violence. If the former is nature's grand fireworks finale, the latter is nature taking the fireworks factory, lighting it all at once, and aiming it straight at the cosmos. When astronomers talk about gamma-ray bursts, they're talking about the undisputed champions of cosmic brightness, the most luminous, high-energy events the universe has ever shown us. And among these dazzling bursts, the ones that last the longest, sometimes tens of seconds, are intimately tied to hypernovae. In fact, the discovery of this link solved one of the greatest astronomical mysteries of the late 20th century. Gamma-ray bursts, or GRBs, were first detected in the late 1960s. Not by astronomers, but by military satellites. The United States had launched the Vela satellites to monitor compliance with the Nuclear Test Ban Treaty, scanning the Earth for gamma-ray flashes from secret atomic detonations. Instead, they started picking up mysterious, fleeting bursts of gamma rays coming from random points in space, far beyond our planet. The signals were brief, sometimes less than a second, sometimes over a minute, but they were astonishingly powerful, releasing more energy in their blink of an eye duration than the sun emits in a year. For decades, No one knew what caused them. They were coming from every direction in the sky, which meant they weren't from our solar system or even from our own galaxy. They were cosmological in origin. But that only deepened the mystery. What could produce that much energy in such a short time? The breakthrough came when astronomers began catching GRBs with afterglows in visible light and radio waves. These afterglows allowed them to pinpoint the burst's host galaxies and measure their distances. Some were billions of light-years away, and yet they were still bright enough for our detectors to pick up instantly. That meant the actual energy output had to be staggering. It was in studying these long-duration GRBs, those lasting more than about 2 seconds, that astronomers began noticing a pattern. Some of them coincided with the appearance of extraordinarily luminous supernovae. Upon closer inspection, these weren't just any supernovae, they were hypernovae. The hypernova's relativistic jets, when pointed toward Earth, were the source of the GRB. Here's how it works. When a massive star collapses into a black hole in a hypernova, much of the infalling material forms a rapidly spinning accretion disk around the newborn black hole. This disk generates colossal magnetic fields that channel some of the energy into twin jets of matter and radiation. These jets punch their way through the star's outer layers and, once they escape into space, they emit gamma rays with extraordinary intensity. Because the jets are so narrow, the radiation is focused into a small solid angle, like a flashlight beam rather than a bare light bulb, which makes them appear even brighter to anyone in their path. To an observer whose line of sight happens to align with one of these jets, the burst of gamma rays is blinding, cosmically speaking. For the brief duration of the GRB, it can outshine the entire rest of the observable universe in gamma ray wavelengths. This is not an exaggeration. In gamma rays, a GRB is literally brighter than all the stars, galaxies, quasars, and nebulae combined. The long GRBs connected to hypernovae are distinct from short GRBs, which are usually caused by merging neutron stars or neutron star black hole pairs. Long GRBs can last anywhere from about 10 seconds to several minutes. But in astrophysical terms, even that is the blink of an eye, and yet it is enough to unleash a torrent of energy that carries across billions of light-years. The brightest GRB ever recorded, GRB 221009A, nicknamed the Boat, short for brightest of all time, is believed to have been associated with a hypernova in a galaxy 2.4 billion light-years away. Even from that unimaginable distance, its energy swamped gamma-ray detectors on multiple satellites, and its optical afterglow was visible in small backyard telescopes. If such an event were to occur within a few thousand light-years and aim at Earth, it would not just be an astronomical spectacle, it could be a biological catastrophe. The gamma rays would ionize Earth's upper atmosphere, breaking apart molecules and potentially stripping away the ozone layer, leaving the surface vulnerable to harmful ultraviolet radiation from the sun. Fortunately, hypernovae capable of producing such dangerous GRBs are exceedingly rare, and the odds of one being both close enough and precisely aimed at us are minuscule. Still, the fact that they exist, and that we've seen them, reminds us of just how raw and unfiltered the universe's power can be. The GRB hypernova connection also gives scientists a valuable tool for studying the deaths of the universe's most massive stars. By observing GRBs, astronomers can trace them back to their host galaxies, study the environments in which these giants lived, and even measure their chemical makeup. Each GRB we observe is like a lighthouse flash from the far reaches of space-time, illuminating not just its immediate surroundings but also the properties of the cosmos itself at different epochs in history. So when we say that hypernovae are linked to the brightest events in the universe, we mean it literally. A single one, when its jet is aimed our way, can for a few precious seconds outshine the rest of the observable cosmos, delivering both beauty and danger in a single, concentrated beam of pure energy. The timescale of a hypernova is one of its most mind-bending qualities. For all the grandeur and scale of these explosions, the main event, the actual release of their staggering energy, happens in a shockingly short window. The collapse of the core into a black hole or neutron star. Less than a second. The formation and breakout of the relativistic jets. Seconds to a couple of minutes at most. The peak gamma-ray emission in a GRB associated with a hypernova? Often over in under a minute. It's almost comical to think about, a star that has lived for millions of years, burning brightly in the cosmic night, meeting its end in a violent finale shorter than the time it takes to boil water. This brevity is deceptive, because in those few seconds the star unleashes more energy than our sun will produce over its entire lifetime. It's like the universe is cashing out the star's entire energy budget in one blinding, concentrated burst. But the short duration of the core event is only the first act. The consequences ripple outward for millions, even billions, of years. The blast wave from the hypernova sweeps through the surrounding interstellar medium, compressing clouds of gas and dust, triggering new rounds of star formation. This ripple effect can reshape entire regions of a galaxy. Stars that might never have formed are born in the wake of that shockwave, and with them come new solar systems, new planets, and perhaps new chances for life. Meanwhile, the material hurled outward at a significant fraction of the speed of light spreads across space, carrying with it freshly forged heavy elements: gold, platinum, uranium, and many others. These atoms become part of future generations of stars and planets. They could end up in the crust of a rocky world, in the atmosphere of a gas giant, or even in the chemistry of a living organism. In this way, the brief moment of the hypernova leaves a lasting chemical fingerprint on the universe. The remnant of the explosion, whether it's a black hole or a neutron star, can also persist for eons. A black hole left by a hypernova might go on feeding from the surrounding material, producing powerful X-ray emissions and shaping the dynamics of its local environment. A rapidly spinning neutron star, or magnetar, could flood the cosmos with periodic pulses of radiation, serving as a kind of cosmic beacon for millions of years until it spins down. Even the light from the hypernova itself can continue to affect the universe long after the initial flash fades. As the expanding debris interacts with surrounding material, it produces afterglows in X-ray, optical, and radio wavelengths that astronomers can study for months or years. And if the hypernova is close enough, the light from the explosion might eventually reach other planetary systems, where it could be bright enough to alter night skies, or, if unlucky, affect atmospheres. There's another way the timescale stretches into the deep future. The photons from hypernovae can travel for billions of years before they encounter anything. When we detect one from the far reaches of the cosmos, we are effectively looking back in time, seeing an event that happened long before our solar system even existed. Some of the hypernovae we've observed may have gone off when the first galaxies were still young, and their light has only just reached us. This juxtaposition, the tiny fraction of time in which the explosion happens, compared to the vast stretches of time over which its effects play out, makes hypernovae one of the most dramatic reminders of the universe's strange relationship with time. They are proof that moments matter, that a few seconds in the life of a star can set the course of events for millions of years, shaping the structure, composition, and even the habitability of distant corners of the cosmos. So, while the star's death is swift and merciless, its legacy is anything but fleeting. A hypernova's influence echoes across space and time, woven into the birth of new stars, the makeup of planets, and perhaps even the rise and fall of civilizations. All from an event that, in its most explosive moment, is over before you've even taken your next breath. Imagine standing on a planet in some distant galaxy and witnessing a hypernova as it rips through the void. The star has collapsed, the jets have broken free, and the explosion blossoms into its peak brightness. For a brief, almost impossible moment, it shines as if someone lit up an entire galaxy and funneled its radiance toward you. This is not exaggeration, it is literal astrophysics. At its brightest, a hypernova can outshine billions of suns. That means if you took every single star in our Milky Way, over 100 billion of them, and put all their light together, a single hypernova could equal or even surpass that combined brilliance. In gamma rays, the brightness is even more absurd. To an observer in the path of one of its jets, the energy output is so intense that for a few seconds it can rival the total energy of all the stars in the observable universe, just in that one wavelength range. Let's put that into some human terms, though it's tricky because our senses simply aren't built to handle these scales. The sun is about 400,000 times brighter in our sky than the full moon. If you replace the sun with a hypernova occurring at the same distance, the sky wouldn't just brighten, it would become so searingly luminous that it would fry your retinas instantly. The heat alone would vaporize Earth before you could even react. Now, obviously, hypernovae don't happen that close to us, but it shows how overwhelming their light is compared to what we normally think of as bright. Even at distances of millions of light-years, a hypernova can be visible to the naked eye. That's like lighting a candle and seeing it from across the entire continental United States, not through air, but through the vast, dimming gulfs of intergalactic space. This is why astronomers with ground-based telescopes can sometimes catch the optical afterglow of a hypernova-triggered gamma-ray burst even without specialized instruments, at least in the initial hours after the event. The staggering light output isn't just a spectacle, it has consequences. Radiation pressure from the blast can push surrounding gas and dust away, altering the star-forming potential of its neighborhood. The intense gamma rays, X-rays, and ultraviolet light from the explosion can ionize vast volumes of space, stripping electrons from atoms and changing the chemistry of interstellar clouds. On a habitable planet within range, that level of radiation would almost certainly be catastrophic, stripping away atmospheric protection and exposing the surface to lethal levels of cosmic and stellar radiation. The physics behind such luminosity comes down to the sheer amount of energy released in such a compact time frame. When matter falls into the forming black hole or neutron star, it's not just gravity at work. Magnetic fields and relativistic particle acceleration concentrate and release energy at rates that dwarf anything else in nature. And unlike the Sun, which releases energy steadily over billions of years, a hypernova dumps its energy budget into a cosmic flashbulb that goes off once and never again. For astronomers, this brightness is both a gift and a curse. It means that hypernovae can be detected across immense stretches of space, allowing us to study them from the farthest reaches of the observable universe. But it also means that we're only ever catching them at their most dramatic moments, fleeting, transient events that vanish almost as soon as they appear. By the time we see their light, the explosion itself is long over, and the star that caused it is nothing more than a remnant. When you consider that every atom of gold in your jewelry, every speck of platinum in electronics, may have been forged in an explosion that once blazed brighter than an entire galaxy, the numbers stop feeling like mere statistics. They become a reminder that even the rarest, most violent events in the universe have a way of leaving their mark, sometimes right in the palm of your hand. When a hypernova detonates, it's not just a burst of light and energy. It's a violent, physical upheaval that flings the star's own guts across the cosmos at staggering speeds. The collapse of the core triggers shockwaves that tear through the star's outer layers, unbinding them in a fraction of a second. The energy released doesn't simply radiate outward in photons, it also accelerates vast amounts of matter to a significant fraction of the speed of light. We're talking about billions of trillions of tons of material hurled outward in every direction, like shrapnel from a cosmic grenade. This ejected matter is incredibly hot, so hot that it exists in the form of plasma, a swirling soup of atomic nuclei and free electrons. The temperatures can climb into the billions of degrees, hot enough to rip apart atoms and force nuclei to fuse into heavier and heavier elements. Some of these elements were already forged in the star's core during its lifetime, but the hypernova shockwave finishes the job, creating exotic isotopes and the heaviest naturally occurring atoms in the universe. The sheer scale of the ejection is hard to imagine. The Sun, in all its stability, loses mass slowly over billions of years through the solar wind, a gentle, steady puff. A hypernova, by contrast, can throw off several times the mass of our Sun in one single event, dispersing it into the interstellar medium in minutes. And the speeds. Ordinary supernova ejector might travel at around 10,000 kilometers per second. Hypernova ejector can exceed 30,000 kilometers per second, 10% of the speed of light. At that velocity, you could travel from Earth to the Moon in under 13 seconds. These outward blasting layers crash into the gas and dust that lie between the stars, creating expanding shells of turbulent material. Over time, these shells cool and slow, but they can span light years across, forming spectacular remnants that persist for tens of thousands of years. Such remnants are not just pretty nebulae for astronomers to admire, they're also chemical enrichment engines. The material from the hypernova mixes into the galactic environment, seeding it with heavy elements that will later become part of new stars, planets, and even living organisms. The pattern of ejection isn't uniform. In many hypernovae, much of the material is funneled into narrow jets along the star's rotational axis, where the explosion's energy is concentrated. But other matter is expelled more spherically, creating a complex, asymmetric cloud of debris. These asymmetries can be so pronounced that by studying the shape and speed distribution of the ejector, astronomers can reconstruct details about the original star's rotation, magnetic field, and even the environment it exploded in. What's even more astonishing is that the kinetic energy of this matter, its sheer motion through space, can be comparable to, or even greater than, the radiated energy we see in light. That means that even though we tend to think of a hypernova as a bright event, much of its true power is hidden in invisible momentum, carried by atomic nuclei and subatomic particles streaking across the void. These particles, especially protons and heavier ions, can become part of the ultra-high-energy cosmic rays that bombard the universe, some eventually slamming into Earth's atmosphere. On human scales, it's utterly destructive. If a hypernova went off within just a few dozen light-years and aimed one of its jets toward us, the gamma-ray pulse would be catastrophic. But even without the beam, the shockwave of matter could be deadly to any planetary system unlucky enough to be in the blast zone. The expanding ejector would sweep through with enough force to strip atmospheres, scorch surfaces, and sterilize worlds. Yet from a cosmic perspective, this violent dispersal is also an act of creation. Those atoms, flung at unimaginable speeds into the galaxy, will one day slow, cool, and fall into new formations. The calcium in your bones, the iron in your blood, the gold in your rings, they all began as part of the violent matter ejection from ancient stellar deaths, possibly even hypernovae. In a sense, each of us carries in our body the aftermath of one of the most powerful explosions in the universe. The creation of heavy elements in a hypernova is where cosmic violence turns into cosmic generosity. Long before the explosion, the massive star's core had been running a nuclear furnace for millions of years, fusing hydrogen into helium, helium into carbon, and on through the chain up to iron. But iron is a dead end for fusion. It doesn't yield energy when fused, it consumes it. So when a massive star's core becomes iron-rich, fusion stops, the pressure holding the star up collapses, and gravity takes over. That collapse is the spark for the hypernova, but it's in the chaos of the explosion itself that the universe's rarest and heaviest treasures are born. When the core implodes and the shockwave tears outward, the temperatures and pressures spike to extremes that dwarf even the star's most energetic fusion stages. In these conditions, a process called rapid neutron capture, or the R process, comes into play. Neutrons, produced in staggering numbers during the collapse, slam into atomic nuclei so quickly that the nuclei don't have time to decay before grabbing more neutrons. This rapid stacking of neutrons builds up very heavy, unstable isotopes, which then decay into stable forms of elements far heavier than iron. Gold, platinum, uranium, thorium, these and many other exotic elements trace their origins to such brief but unimaginably intense neutron storms. In just seconds, a hypernova can manufacture more gold than exists in an entire galaxy's worth of planetary crusts. And this isn't just poetic speculation, we've seen the fingerprints. The light spectra of hypernovae and their remnants contain telltale absorption and emission lines corresponding to these heavy elements, confirming that such cosmic foundries are real. But it's not just the R process at work. The explosion also powers the creation of intermediate elements like nickel, cobalt, and copper in enormous quantities. In fact, the brightness of many supernovae, and by extension hypernovae, is partly fueled by the radioactive decay of nickel-56 into cobalt-56 and then into iron-56, releasing energy as gamma rays that keep the debris cloud glowing long after the initial blast. What's fascinating is that the distribution of these heavy elements across the universe tells us a story of countless stellar deaths before our sun ever existed. The ancient stars that went hypernova billions of years ago enriched the clouds of gas and dust that later collapsed to form our solar system. Every atom of gold in your jewelry, every grain of uranium in the Earth's crust, every speck of platinum in electronics, all of it is a relic of a star's death throes. Without hypernovae and similar cataclysmic events, the periodic table as we know it would be incomplete, and life, at least life that depends on chemistry like ours, would be impossible. There's an irony here. The very elements we often associate with stability and permanence, gold that resists tarnish, uranium that can remain in rock for billions of years, were created in the most unstable and fleeting of environments. In just a few heartbeats of cosmic time, the universe forges them in a crucible of collapsing matter, only to fling them out into the galaxy to cool and condense over eons. This process also helps astronomers piece together the chemical history of galaxies. By measuring the abundance of heavy elements in ancient stars, researchers can infer how many hypernovae must have occurred in the early universe, and what kinds of stars were responsible. This is part of why studying these explosions isn't just about understanding extreme physics, it's also about understanding where we come from. In a very literal sense, we are walking, breathing monuments to hypernovae. The iron in your blood allows oxygen to bind and sustain your life. The calcium in your bones, the copper in your nervous system, the gold on your finger, all were forged in a furnace that tore a star apart and lit up the universe. It's hard to imagine a more spectacular origin story for the atoms that make us. When a hypernova erupts, the blast we see is only half the story. Hidden at the very heart of the event, in the split second before the outer layers are blown away, the core of the massive star undergoes one of the most extreme transformations in nature. It collapses into a black hole. This birth is as sudden as it is violent. The star's gravity, no longer countered by the outward pressure of nuclear fusion, crushes the core inward at a significant fraction of the speed of light. As it falls, matter becomes so densely packed that atomic nuclei themselves are forced together, electrons and protons merge into neutrons, and the density skyrockets beyond anything we can comprehend. If the collapsing mass is above a certain threshold, around 3 times the Sun's mass, nothing can stop the collapse. Not even neutron degeneracy pressure, the quantum force that props up neutron stars, can resist it. The result is a singularity, a point where space and time themselves are bent into an infinitely dense knot, surrounded by an event horizon from which nothing, not even light, can escape. This newborn black hole isn't just sitting quietly while the rest of the star explodes, it's actively shaping the hypernova. Matter falling toward the event horizon releases enormous gravitational energy, some of which powers the colossal relativistic jets that spear out along the star's axis. These jets, racing outward at nearly the speed of light, are what give us the intense gamma-ray bursts linked to many hypernovae. The black hole's creation is inseparable from the explosion's most spectacular features. Interestingly, not every hypernova makes a black hole. If the collapsing core is just under the critical mass, it can halt at the neutron star stage, an incredibly dense sphere only about 20 kilometers wide but more massive than our Sun. However, in the most massive progenitor stars, black hole formation is almost inevitable. And for the largest of these, the process might skip the neutron star phase entirely, plunging straight from collapsing iron core to black hole in milliseconds. The creation of a black hole marks the point of no return for the star. Its light, its nuclear reactions, its stellar winds, all the processes that defined its life are over. The black hole, unlike the bright star it came from, is invisible except for the effects it has on its surroundings. If it accretes leftover material from the explosion, it can flare back to life in bursts of X-rays or even reignite jets. But these are flickers compared to the star's final explosion. From a cosmic perspective, the birth of a black hole in a hypernova is both an ending and a beginning. It's the end of the star's story, but it's also the creation of one of the universe's most mysterious objects, one that can persist for trillions of years, long after the galaxies themselves have faded. Some of these stellar mass black holes may later merge with others, producing gravitational waves detectable across billions of light-years. In this way, the hypernova not only seeds the universe with heavy elements, but also leaves behind a silent, enduring legacy in the form of a black hole. There's something poetic in that. The brightest explosion in the universe can give birth to the darkest object imaginable, a place from which no light escapes. The hypernova's light may fade within weeks or months, but the black hole it leaves behind will outlast everything else, an invisible monument to the violence that created it. Hypernovae don't just happen down the galactic street, they are events that usually occur at staggering distances from us, so far away that their light can take millions, sometimes even billions, of years to reach Earth. When astronomers detect the glow from one, they're not witnessing something that's happening right now, they're looking back through time, seeing the event as it occurred long before humans, or even our planet, existed. If a hypernova erupted in a galaxy a billion light-years away, the photons from that blast would have begun their journey back when life on Earth was still single-celled and drifting in ancient seas. Those photons traveled through the cosmic web, weaving between galaxies, avoiding capture by dust or deflection by gravity wells, only to finally collide with the mirrors and sensors of our telescopes in the present day. This is why each detection feels like a cosmic time capsule. We're opening a window onto a moment in deep history. The distances are so great that even the most powerful explosions ever recorded appear as mere points of light through our best telescopes. A hypernova that outshines an entire galaxy up close may look like nothing more than a faint, flickering star in our instruments. It's the spectrum, the timing, and the high-energy signatures like gamma-ray bursts that reveal the true nature of what we're seeing. Without these tools, a hypernova in a distant galaxy could be easily mistaken for something far less extraordinary. Yet the fact that we can see them at all from such immense distances speaks to just how mind-bendingly powerful they are. A typical star is visible only if it's relatively close to our galaxy, but a hypernova can blaze across the universe, outshining billions of ordinary stars combined. Some gamma-ray bursts linked to hypernovae have been detected from more than 10 billion light-years away, meaning they happened when the universe was less than a quarter of its current age. That's like spotting a candle flame on the other side of a continent, and having it still blind your eyes for a moment. From a safety standpoint, the sheer distances are reassuring. Most hypernovae are so far away that their energy, however colossal, dissipates harmlessly before reaching us. Even the lethal beams of gamma radiation from their jets, which could strip a planet's atmosphere if it were too close, fade to negligible levels by the time they've crossed millions of light-years. We can study them without fear, admiring the fire from the far side of the cosmic forest. These great distances also mean that every hypernova we see is part of a vast cosmic pattern. They're not just explosions, they're markers of where massive stars once lived and died. By mapping their locations in distant galaxies, astronomers can trace the regions of intense star formation across cosmic history. When we spot a hypernova in a galaxy billions of light-years away, we're effectively seeing where giant stars were being born in the early universe and how galaxies evolved over time. And there's a humbling thought here. The light from a hypernova billions of light-years away began its journey long before our solar system formed. By the time it arrives, the star that created it has been gone for eons, its debris scattered, its black hole quietly orbiting or wandering the galaxy. What we witness is a ghost of something that existed in a completely different cosmic era, a postcard from a universe that no longer exists in the form we see it. For all their distant beauty, hypernovae carry a hidden menace, one that, if unleashed too close to home, could rewrite Earth's history in an instant. The danger comes not from the light we can see, but from the invisible fury of their gamma-ray bursts. A gamma-ray burst, or GRB, is essentially the universe's most intense flash of high-energy radiation. In a hypernova, especially one that collapses into a black hole, enormous jets of matter and energy are fired from the poles of the collapsing star at nearly the speed of light. These jets are narrow, often only a few degrees across, but within those beams lies more concentrated power than the Sun will emit in its entire 10 billion-year lifetime. If Earth were unlucky enough to be in the direct path of one of these beams, even from thousands of light-years away, the results could be catastrophic. The intense gamma rays would slam into our upper atmosphere, breaking apart nitrogen and oxygen molecules and creating a haze of nitrogen oxides. This chemical chain reaction could strip away much of the ozone layer in mere seconds, leaving the surface exposed to lethal ultraviolet radiation from the sun. Without that protective shield, ecosystems would collapse, food chains would shatter, and mass extinctions would follow. The frightening part is that we wouldn't have much warning. A GRB's radiation travels at the speed of light, so the moment we detect it is the moment it arrives. The burst itself might last anywhere from a couple of seconds to a few minutes, but the atmospheric damage it causes could last for years. Astronomers believe that such an event may have contributed to one of Earth's mass extinctions hundreds of millions of years ago, although direct evidence is hard to confirm. Thankfully, hypernovae, and their deadly gamma-ray beams, are rare. In our Milky Way galaxy, they might occur only once every few million years. And because the jets are so tightly focused, the odds of one pointing directly at Earth are vanishingly small. We're talking lottery-level chances, except the stakes aren't money, they're planetary habitability. Still, astronomers keep an eye on potential candidates. Stars like Eta Carinae, a colossal stellar giant about 7,500 light-years away, are often discussed in this context. While Eta Carinae is indeed massive enough to end in a hypernova, current models suggest that even if it does produce a GRB, its rotation axis, and thus its deadly beam, probably won't align with Earth. But probably is one of those words that keeps scientists from sleeping too soundly. The danger isn't limited to direct hits, either. Even if Earth were off to the side of a hypernova's beam, a close enough event could still flood our planet with enough radiation to disrupt satellites, damage electronics, and cause biological harm to high-altitude life. In a worst-case nearby scenario, within a few dozen light-years, life as we know it could face a near-total wipeout. Yet here's the twist. Without such cosmic violence, we wouldn't be here in the first place. The same hypernovae that could sterilize planets are the ones that create the heavy elements necessary for life. It's a delicate balance. The universe's most destructive events are also its most creative. We're alive because countless hypernovae have already burned across space, but our survival depends on the next one being very, very far away. Spotting a hypernova is a bit like trying to catch a lightning strike on the far side of the world. You can't predict exactly when or where it will happen, and when it does, it's over almost instantly. Yet astronomers have developed an intricate, global watch system that allows us to capture these fleeting cosmic events in astonishing detail. The first clue often comes from space-based gamma-ray observatories. Because gamma rays can't penetrate Earth's atmosphere, satellites like NASA's SWIFT and FEMI are our eyes in the high-energy universe. They continuously scan the sky, waiting for sudden spikes of gamma radiation. When one of these spikes appears, lasting seconds or minutes, it sets off an automated alert. This alert is transmitted to astronomers all over the world in real time, sometimes within seconds of the initial burst. These alerts trigger a coordinated observational sprint. Ground-based telescopes swing into position, aiming at the patch of sky where the burst originated. Since gamma rays arrive first, optical and radio telescopes then look for the afterglow, the fading light across different wavelengths as the hypernova's shockwave expands and collides with surrounding gas. These afterglows can last hours, days, or even weeks, giving scientists a chance to measure the distance, brightness, and energy output of the event. One of the biggest challenges is pinpointing the exact source. Gamma-ray detectors can localize the event only to a relatively broad area of the sky. That's why the follow-up work is so critical. Optical surveys like those from the Pan-STARRS telescope in Hawaii or the Zwicky Transient Facility in California scour the region for a new point of light that wasn't there before. If they find one, astronomers compare its spectrum to known supernova patterns, and if the energy profile is extreme enough, it's flagged as a hypernova candidate. Spectroscopy is the key to confirmation. By splitting the light into its component wavelengths, scientists can see the unique fingerprints of elements present in the explosion's debris. Certain patterns, such as unusually high expansion velocities or specific lines from heavy elements, help distinguish hypernovae from more common supernovae. And because light is redshifted by the universe's expansion, these spectra also tell us how far away the event is, which in turn lets us calculate its true energy output. The process has become even more powerful in the era of all-sky monitoring. Automated systems now patrol the heavens nightly, taking rapid snapshots of huge swaths of sky. Software compares each image to previous ones, instantly flagging anything new or changing. This means that even if a hypernova doesn't produce a detectable gamma-ray burst, perhaps because its jet isn't pointed at us, it can still be discovered from its visible light signature alone. The sheer coordination involved is staggering. Sometimes, dozens of observatories across multiple continents will train their instruments on the same patch of sky, covering every wavelength from radio waves to X-rays. Even amateurs with backyard telescopes sometimes join in, capturing valuable data during the first hours after detection. In these moments, the entire astronomical community becomes a single, synchronized network, all working to squeeze every last bit of information out of a cosmic flash that might never happen again in that exact spot. And beyond our human efforts, machine learning is now stepping in. Artificial intelligence is being trained to recognize hypernova patterns faster than humans can, sifting through millions of data points to catch subtle early signs before the main event peaks. With the upcoming Vera C. Rubin Observatory, expected to take a complete map of the entire visible sky every few nights, our chances of catching hypernovae in the act are about to increase dramatically. In the end, detecting a hypernova isn't just about catching a distant explosion, it's about catching a moment of cosmic history, a flash of light that's been racing toward us for millions or billions of years, only to meet our gaze for a brief instant before fading forever. Every detection is a conversation across time and space, a whisper from a star long dead but still telling its story. Some hypernovae live only in theory and simulation, but others have left such an unmistakable mark on our observations that they've become legendary in astronomy. Among these, two events, GRB 980425 and SN 1998BW, stand out as milestones, not just for their sheer power, but because they helped bridge the gap between two of the most mysterious cosmic phenomena ever studied, long-duration gamma-ray bursts and hypernovae. It all began on April 25, 1998, when a sudden burst of gamma rays was detected by the Beppo SAX satellite. The event was catalogued as GRB 980425, and at first, it seemed peculiar. Compared to many other gamma-ray bursts, it was relatively weak in terms of its gamma-ray output, which puzzled scientists. But the real intrigue came when telescopes pointed toward its origin and discovered something extraordinary: a bright, new optical source in a nearby galaxy, just 140 million light-years away. This was not the usual case. Most gamma-ray bursts were found much farther out in the universe. That new optical source turned out to be a hypernova, later designated SN 1998BW. And it wasn't just any hypernova. It was unlike anything astronomers had seen before. The explosion was far more luminous than a typical supernova, with an energy release so vast it redefined expectations. Its spectrum revealed extremely fast-moving ejecta, traveling at a significant fraction of the speed of light, and unusual chemical signatures hinting at an exotic origin. What made this pairing groundbreaking was the fact that GRB 980425 and SN 1998BW were linked in both time and location. For the first time, astronomers had solid evidence that at least some long-duration gamma-ray bursts were directly tied to the death of massive stars in hypernova explosions. This connection wasn't just a coincidence, it was a smoking gun in the mystery of GRB origins. Before this discovery, gamma-ray bursts were one of astronomy's great puzzles. They appeared as random flashes from deep space, lasting from a fraction of a second to several minutes, with no clear explanation for their cause. The link to SN 1998BW suggested that in certain massive star deaths, the collapsing core forms a black hole, and twin relativistic jets punch through the star's outer layers, producing a burst of gamma rays. The accompanying hypernova is the visible aftershock, the lingering light after the high-energy flash. SN 1998BW also defied another expectation. It was close enough for detailed study. Most gamma-ray bursts happen billions of light-years away, so by the time their light reaches us, it's faint and hard to dissect. But this event occurred in the relatively nearby galaxy ESO 184G82, allowing astronomers to watch it evolve in unprecedented detail. They tracked the brightening and fading over weeks, mapped its energy distribution, and studied the debris cloud as it expanded into space. The hypernova's luminosity was staggering. It briefly shone brighter than the entire galaxy that hosted it. And while the gamma-ray burst itself was weaker than the most powerful ones we've seen, the combination of events gave us the first tangible link between two of the universe's most violent processes. It was as if two previously separate mysteries suddenly revealed they were chapters of the same story. Today, GRB 980425 and SN 1998BW are taught in astrophysics as a cornerstone case study. They prove that hypernovae are not just theory, they are real, measurable, and directly observable. They showed that some gamma-ray bursts are the opening act of a massive stellar collapse, and that the afterglow we see in optical light is the signature of a star's complete, catastrophic end. And perhaps most importantly, they reminded astronomers of a humbling truth. Sometimes the universe gives you just the right event at just the right distance, offering a rare, fleeting opportunity to connect the dots across cosmic scales. Without SN 1998BW, the link between hypernovae and gamma-ray bursts might have remained speculative for decades longer. When we talk about the energy of a hypernova, the numbers get so big they almost stop making sense. It's like trying to imagine the weight of a mountain in terms of feathers. You can say the number, but your brain rebels against truly grasping it. So, let's anchor it in things we can at least partially relate to, even if those comparisons still stretch the imagination to its breaking point. Start with our Sun. Over its entire 10 billion year lifetime, the Sun will radiate about 1.2 times 10 carat 44 joules of energy. That's every photon, every sunbeam, every particle of solar wind, every moment it will ever shine. A hypernova can release that much energy in a matter of seconds or minutes. It's as if you compressed the Sun's entire multi-billion-year existence into a single breath of cosmic fury. Now let's scale down to something human-made, the most powerful nuclear bomb ever detonated on Earth, the Tsar Bomba. It yielded about 2.1 times 10 carat 17 joules of energy, enough to level entire cities and shatter windows hundreds of kilometers away. To match the energy of a hypernova, you would need to detonate Tsar Bomba not just once, not just thousands of times, but billions upon billions of times every second for several minutes straight. It's an absurd figure, So absurd it makes even the term weapon of mass destruction feel like a child's firecracker in comparison. Even regular supernovae, which are already mind-bogglingly powerful, pale beside a hypernova. A normal supernova releases about 10^44 joules in total energy, but much of that comes in the form of neutrinos that we can't directly see. Hypernovae not only match or exceed that total, they also put far more of their energy into visible and high-energy light, making them dazzlingly bright. Some estimates place the kinetic energy of the material hurled outward by a hypernova at 10 times that of a typical supernova, which means far more devastation for the surrounding cosmic neighborhood. In human terms, the numbers become laughably unrelatable. A hypernova can, for a brief moment, outshine entire galaxies that contain hundreds of billions of stars. Imagine every single light bulb on Earth suddenly becoming as bright as the sun, and then imagine that multiplied by billions. That's the scale we're talking about. This isn't just power, it's ultimate power, power that reshapes its surroundings for millions of years. The energy shockwave from a hypernova can trigger star formation by compressing gas clouds, or it can strip those clouds away entirely, halting star birth in a region. It can scatter heavy elements across vast stretches of interstellar space, seeding future solar systems with the raw materials for planets and life. Its creation and destruction wrapped into a single detonation. And the most incredible thing? All of that energy comes from one star, a single object in the cosmos reaching the end of its life and collapsing under its own gravity. There are no massive engines, no alien technology, no artificial amplification, just nature, following the laws of physics, producing a light show so intense it can be seen from billions of light years away. It's here that you start to appreciate why astronomers speak about hypernovae with a mix of awe and reverence. We throw around the word powerful a lot. Powerful storms, powerful machines, powerful computers. But in the cosmic dictionary, powerful finds its final, most uncompromising definition in the hypernova. Its energy on a scale that humbles even the most ambitious human achievements, a raw display of the universe's ability to completely dwarf us without even trying. If normal supernovae are the universe's fireworks, then hypernovae are its once-in-a-century, city-stopping, sky-filling superdisplays. Except the scale is cosmic, and the rarity is even more extreme. While supernovae themselves are already relatively uncommon on human timescales, occurring only a few times per century in a typical galaxy, hypernovae are an entirely different level of scarcity. To put it in perspective, astronomers estimate that for every 1,000 core-collapse supernovae, maybe one, or in some galaxies, even fewer, will be a hypernova. That means that in the Milky Way, where a core-collapse supernova might happen once every 50 to 100 years, we could expect a hypernova only once every several 100,000 years. In human terms, this is like waiting through all of recorded history several times over just to see one event. This rarity stems from the extreme conditions required to produce a hypernova. First, the progenitor star has to be enormously massive, often more than 30 times the mass of our Sun. These stars are rare to begin with, because the universe simply doesn't form very many of them. Most stars are far smaller and live much longer. Massive stars also burn through their fuel incredibly quickly, living only a few million years compared to the billions enjoyed by smaller stars, which means they spend less time existing in the universe at all. Then there's the matter of rotation and magnetic fields. Not every massive star that dies produces a hypernova. Many just collapse into an ordinary supernova. For a hypernova to occur, the star's core often needs to be spinning rapidly, with strong magnetic fields capable of focusing energy into powerful jets. If those conditions aren't met, the explosion might still be bright and impressive, but it won't reach hypernova levels. The angle from which we observe them also plays a role. Some hypernovae are accompanied by long gamma-ray bursts, but those bursts are highly directional. If the jet isn't aimed toward Earth, we may never detect the gamma-ray component, and the optical light alone might not be enough for us to confidently identify it as a hypernova. That means the number we've observed so far could be an underestimate. There might be more of them out there that simply went off in directions we weren't looking. Astronomers sometimes call hypernovae cosmic lottery wins, in the sense that catching one is partly a matter of patience and partly pure luck. Large-scale sky surveys increase our chances of spotting them, but even then, the combination of rarity, distance, and fleeting brightness makes them elusive targets. When one does appear, it becomes an all-hands-on-deck situation in the astronomy community, because everyone knows that once it fades, the opportunity is gone forever. Their rarity also has an upside. It's part of why we're still here. If hypernovae were as common as supernovae, the intense gamma-ray bursts and radiation they emit could be far more threatening to life in many regions of the universe. In fact, some scientists speculate that in other galaxies, or even earlier in our own galaxy's history, hypernovae might have periodically sterilized entire swaths of space, influencing where and when life could arise. So when we talk about hypernovae, we're not just talking about power, we're talking about cosmic events so uncommon that witnessing one is like being present for the rarest natural wonders the universe can offer. They are the fleeting, unpredictable, yet unforgettable beacons of stellar death, illuminating the cosmos for an instant before vanishing into memory. Hypernovae may be rare, but their influence echoes through galaxies for millions, even billions, of years. They're not just spectacular fireworks marking the death of a massive star. They're architects and sculptors of the galactic environment, shaping where and how future stars and planets will form. In many ways, they are both the undertakers and the gardeners of the cosmos, clearing space and planting seeds for the next generation of stars. When a hypernova detonates, it releases an enormous shockwave that travels outward at thousands of kilometers per second. This wave doesn't just passively move through the interstellar medium, it rams into it with such force that it can radically change its structure. Dense molecular clouds, the raw material for star formation, can be compressed by this blast, causing regions of gas to collapse under their own gravity and ignite into new stars. In this sense, a hypernova can kickstart entire stellar nurseries, triggering a burst of star birth in its aftermath. But there's a flip side. The same shockwave, depending on its speed and intensity, can also blow apart fragile clouds of gas before they have a chance to collapse. This can quench star formation in a region, stripping it of the raw materials necessary for creating new suns. Whether a hypernova triggers or suppresses star formation often depends on the density and arrangement of the surrounding gas at the time of the explosion. Over larger scales, repeated stellar explosions, including the occasional hypernova, help regulate the cycle of matter in galaxies. They drive vast streams of gas, called galactic outflows, that can extend tens of thousands of light-years beyond a galaxy's visible disk. In extreme cases, these outflows can carry away so much material that they alter the galaxy's future growth, slowing or even halting the rate of star formation for millions of years. Hypernovae also play a unique role in distributing heavy elements. The blast scatters freshly forged metals like gold, platinum, and uranium far into interstellar space. Over time, these elements mix with other gas clouds, ensuring that the next generation of stars, and their planets, are richer in the chemical diversity needed for complex chemistry and potentially for life. In the early universe, when the first hypernovae exploded from massive, short-lived stars, they may have been among the primary sources of heavy elements in the cosmos. The scale of their influence is hard to overstate. Imagine a single explosion sending ripples through the structure of a galaxy, setting off chain reactions of creation and destruction that play out long after the original star is gone. Over billions of years, these effects accumulate. The very structure of spiral arms, the thickness of galactic disks, and even the chemical composition of stars today are partially shaped by countless stellar deaths, with hypernovae among the most potent contributors. They also act as cosmic markers for astronomers. When we detect the remnants of an ancient hypernova, whether as a nebula rich in heavy metals or as a black hole drifting through space, we gain clues about a galaxy's past. By studying the distribution and composition of these remnants, scientists can reconstruct periods of intense star formation or galactic mergers that might have triggered the creation of massive stars capable of ending their lives as hypernovae. In short, while hypernovae are isolated events in both time and space, their fingerprints are found throughout the architecture of galaxies. They help determine which regions become bustling stellar cities and which remain dark and empty. They enrich the cosmic canvas with the elements needed for planets, oceans, and possibly life. And, over the eons, they weave their influence into the very fabric of galactic evolution, proving that even the most violent ends can be the beginning of something new. When a hypernova erupts, it's not just a spectacle for distant astronomers, it's a lethal event for anything unlucky enough to be nearby. The energy released is so overwhelming that it can strip away atmospheres, bombard planets with deadly radiation, and sterilize entire star systems in a cosmic instant. We often think of space as being so vast that nothing can reach across it to harm us, but a hypernova is proof that danger can travel light years without losing its potency. The most dangerous aspect, especially for life, isn't just the visible light, it's the high-energy radiation, particularly gamma rays. If the hypernova produces a gamma ray burst, those beams can stretch across enormous distances, traveling in a straight, unforgiving line at the speed of light. A planet caught in the direct path of one of these beams is in serious trouble, even if it's dozens of light years away. Here's why. Gamma rays are incredibly energetic photons. They can break apart molecules in an atmosphere, particularly the ozone layer on a planet like Earth. The ozone layer acts as a shield, blocking harmful ultraviolet, UV, light from a star. If that shield is stripped away, the planet's surface becomes bathed in lethal UV radiation, which can kill microorganisms, disrupt ecosystems, and potentially wipe out higher forms of life in a matter of years or even months. Some scientists have proposed that events like this may have occurred in Earth's past. There's speculation that a mass extinction around 450 million years ago, the late Ordovician extinction, might have been triggered by a gamma-ray burst or another high-energy cosmic event. The evidence isn't conclusive, but it shows how seriously researchers take the possibility. The kill zone of a hypernova depends on its energy and the intensity of any gamma-ray burst it produces. For a truly extreme event, the direct danger range could be tens of light years, possibly more. Within that zone, planets might lose their atmospheres entirely, their surfaces scorched by both the initial radiation and the prolonged bombardment from their own now unshielded stars' UV rays. Even outside the immediate kill zone, the shockwave and cosmic rays from the explosion could have long-term effects on planetary climates and biospheres. It's also worth noting that hypernovae can sterilize regions indirectly. By blasting nearby gas clouds with intense radiation and shockwaves, they can disrupt the environments where planets and stars are forming, altering the chemical balance and preventing the kind of stable conditions needed for life to get a foothold. Thankfully, the sheer rarity of hypernovae makes this an unlikely threat for Earth in the foreseeable future. The closest known massive stars that could one day become hypernovae, like Eta Carinae, are far enough away that even if they exploded, they wouldn't pose a direct danger to us. But on the cosmic scale, there are undoubtedly worlds that have been unlucky enough to be in the wrong place at the wrong time, their histories and potential for life erased in a flash. In this way, hypernovae are both creators and destroyers. The same blast that seeds the galaxy with life's building blocks can also extinguish life instantly, making them one of the most paradoxical forces in the universe. They're a reminder that in space, survival sometimes depends not on strength or adaptation, but on sheer cosmic luck, being far enough away when a giant star decides to die in the most spectacular way possible. Looking at a hypernova today is a bit like opening a time capsule from the earliest days of the universe. These colossal explosions don't just tell us about a single star's violent death, they offer a window into the kinds of stars that lived, burned, and died billions of years ago, back when the cosmos was young and its first galaxies were still taking shape. The key is that hypernovae often originate from stars that resemble the earliest stellar generations in terms of size and mass. In the early universe, right after the Big Bang, the chemical makeup of space was extremely simple, mostly hydrogen and helium, with just trace amounts of lithium. The first stars, called population 3 stars, were forged from this pristine material. Without heavy elements to help cool the gas, these stars could grow far larger than most stars today, sometimes hundreds of times the mass of the Sun. Many of them likely lived short, brilliant lives before ending in explosions similar to, or even more extreme than the hypernovae we observe now. The trouble is, we can't directly see these first stars, they burned out billions of years ago. But hypernovae act as modern analogues. By studying them, astronomers can reconstruct the chain of events that might have occurred in the early cosmos. The chemical fingerprints left in a hypernova's light spectrum, patterns of absorption and emission at specific wavelengths, reveal which elements were produced during the explosion and in what quantities. These fingerprints give clues about the star's original composition and, by extension, about the chemical state of its surrounding environment before it died. Even the distribution of elements tells a story. Early hypernova-like explosions would have been crucial for spreading heavy elements into space, enriching the interstellar medium and enabling later generations of stars to form planets, oceans, and eventually life. By comparing the elemental ratios from modern hypernova remnants with those found in ancient stars in our galaxy's halo, stars that have remained chemically untouched since their formation, astronomers can piece together a timeline of cosmic enrichment. Hypernovae also help researchers understand the role of rotation and magnetic fields in early massive stars. Many early universe stars may have spun faster due to differences in their formation conditions. The relativistic jets we see in some modern hypernovae could mimic the intense outflows that shaped galaxies in their infancy. This means hypernova research isn't just about individual explosions, it's about galaxy-scale evolution across cosmic history. And then there's the simple fact of distance. Some hypernovae we detect are so far away that their light left the explosion billions of years ago, when the universe was still young. Observing them is literally seeing into the past. The faint signals captured by space telescopes like Hubble or the James Webb Space Telescope act as time machines, letting us witness events that happened when the first large-scale cosmic structures were forming. In essence, hypernovae are among our best natural laboratories for studying conditions we can't otherwise access. They're violent, yes, but their chaos carries within it the data we need to understand where we came from, both chemically and cosmically. Each one is a flash of ancient truth, a brief moment when the deep past spills into our present, illuminating the story of a universe still in its earliest chapters. When physicists talk about the most powerful explosions in the universe, hypernovae inevitably come up, but they also can't resist asking the next question. Is there a ceiling to how big these explosions can get? Is there some ultimate upper limit to the energy nature can pack into a single stellar death? Or could there be events out there beyond anything we've ever imagined? At first glance, it seems like there should be a limit. After all, a star's total energy budget is dictated by its mass, and mass isn't infinite. Even the largest known stars in today's universe, like the behemoths over 200 times the Sun's mass, can only store so much nuclear fuel in their cores. Once that fuel is gone, the way the star dies depends on how it collapses, how much of its outer layers it sheds, and whether its core forms a black hole, a neutron star, or something else. For hypernovae, the most extreme cases we've observed release on the order of 10 to the power of 45 joules of energy, hundreds of times more than a standard supernova. But could we double that? Multiply it by 10? In theory, yes, if you start with a star that's even bigger, with conditions that allow it to explode rather than simply collapse into a black hole without much fuss. Some astrophysicists point to pair-instability supernovae as a hint at the theoretical maximum. These explosions occur in stars so massive, over about 130 times the Sun's mass, that the intense gamma rays in their cores start producing matter-antimatter pairs, which destabilizes the star completely. In such a case, the entire star can be blown apart in one titanic event, leaving no black hole behind. While these are not technically the same as hypernovae, they suggest a pathway to energy releases on par with or exceeding the biggest hypernovae we've recorded. But there's a catch. The early universe likely had more massive stars capable of such endings, but in our modern, metal-rich cosmos, stars lose mass rapidly through powerful stellar winds. This mass loss limits how big they can get before their death. That's why some scientists argue we may already be seeing the practical upper limit for explosion energy in the universe today. Nature simply doesn't make stars large enough anymore to exceed it by much. Others counter that there could be exotic scenarios we haven't yet witnessed. Collapsars, for example, hypernovae linked to massive stars collapsing into black holes with high spin, could, under the right conditions, produce even more energetic gamma-ray bursts than anything currently observed. Some even speculate about supercollapsars involving stars with extreme rotational energy and magnetic fields, producing ultra-relativistic jets far beyond our current scale of measurements. And then there's the tantalizing possibility of explosions involving phenomena outside of normal stellar evolution, events tied to exotic physics like quark stars, hypothetical objects even denser than neutron stars. If such stars exist and were to explode, they might challenge our current definitions of what's possible. For now, the upper limit remains a subject of lively debate. Every time astronomers spot an unusually bright gamma-ray burst or a supernova remnant with unexpected characteristics, the question gets raised again. Is this it? Is this the top of the cosmic power scale? Or is it just another stepping stone toward an even bigger discovery? In a way, the fact that we don't know is part of the thrill. Hypernovae already operate at the ragged edge of known physics, so the idea that there could be something beyond them, some ultimate, universe-shaking explosion yet to be seen, keeps both theorists and observers watching the skies with a mix of scientific rigor and childlike wonder. Until we find it, or prove it can't exist, the search for the true limits of cosmic power will go on. If hypernovae are the rock stars of the cosmic explosion world, then perinstability supernovae are their rare, elusive cousins, the ones who show up once in a cosmic lifetime, blow the roof off the universe, and then vanish without leaving so much as a black hole behind. They're not exactly the same thing as hypernovae, but they belong in the same family of stellar cataclysms, and in some respects, they push the boundaries of how completely a star can obliterate itself. The concept is rooted in a fascinating bit of high-energy physics. In most supernova scenarios, the core collapse is halted, at least for a moment, by neutron degeneracy pressure or other quantum effects. In hypernovae, you often end up with a black hole or neutron star as the leftover remnant. But in a pair-instability supernova, the star sidesteps all of that. Instead, it destroys itself so thoroughly that nothing is left behind. No core, no neutron star, no black hole, just an expanding cloud of stellar guts hurled into the void at ridiculous speeds. Here's how it happens. These supernovae begin with a star of extraordinary mass, typically between 130 and 250 times the mass of our Sun. The temperatures in the core become so extreme, hundreds of millions of degrees, that the photons inside have enough energy to spontaneously transform into matter-antimatter pairs, electrons and positrons. This is what astrophysicists call pair production. Under normal circumstances, radiation pressure from high-energy photons helps counteract the force of gravity inside the star, keeping it from collapsing. But when a significant portion of that photon energy is suddenly converted into particle pairs, the radiation pressure drops dramatically. The star's delicate balancing act collapses, gravity wins instantly, and the core starts to implode. But instead of leading to a neat, compact remnant, the implosion triggers runaway fusion reactions, burning oxygen and silicon in a violent, uncontrolled burst that blow the entire star apart. The energy released in a pair-instability supernova can be on par with, or even greater than, the largest hypernovae we've observed, but the real kicker is the sheer mass of material ejected. Hundreds of solar masses of gas and newly forged heavy elements are flung into space, enriching the surrounding interstellar medium on a massive scale. It's like nature's way of pouring an entire periodic table into the galaxy in one go. Astronomers think these explosions were far more common in the early universe, when the first generations of stars, population 3 stars, could grow to enormous sizes without losing too much mass through stellar winds. In today's universe, where stars form with higher metallicity, meaning they have more elements heavier than helium, strong winds strip away much of that mass before they can reach the required size for a pair-instability supernova. That's why they're so rare now, and why finding one would be like uncovering a fossil from the dawn of time. There have been a few candidates for modern pair-instability events. SN 2007 Bi, for example, caught astronomers' attention for its incredible brightness and slow fade, both of which matched theoretical predictions. But these identifications are tricky. Observations have to be painstakingly compared with models, and sometimes what looks like a pair-instability event can turn out to be a different kind of extreme supernova powered by other mechanisms, like magnetars. Even so, studying these rare explosions isn't just academic curiosity. They tell us about the mass limits of stars, the physics of matter under insane conditions, and the way heavy elements are seeded throughout the universe. They're also a tantalizing reminder that the diversity of stellar deaths is wider than we once thought, and that even in a universe full of fireworks, there are still new kinds of blasts waiting to be understood. One of the most intriguing aspects of hypernovae is that they don't just explode in all directions like a simple, spherical bomb in space. Instead, many of them unleash narrow, focused beams of energy, relativistic jets, that pierce through the collapsing star and shoot out into the universe at nearly the speed of light. These jets aren't just a side effect, they may be the very engines that make hypernovae as powerful and spectacular as they are. Imagine the scene deep inside a dying massive star. Its core has collapsed, forming either a newborn black hole or an extremely dense neutron star, spinning at incredible speeds. Around this compact object, a dense accretion disk of infalling stellar material forms. Magnetic fields in this disk become twisted and amplified to unimaginable strengths. Under these extreme conditions, something remarkable happens. Some of the collapsing matter doesn't fall in at all, but is instead funneled along the star's rotational axis, where magnetic forces and radiation pressure accelerate it into ultra-fast, highly collimated jets. These jets are not gentle breezes. They are narrow streams of plasma and high-energy radiation moving so close to the speed of light that relativity comes into play in a big way, hence the term relativistic jets. And because they are so tightly focused, they can carry a huge fraction of the explosion's total energy in just a small fraction of the solid angle around the star. It's like focusing the power of an entire nuclear arsenal into the tip of a laser pointer. When these jets burst through the star's outer layers, they release titanic amounts of gamma rays, the highest energy form of light we know. This is why hypernovae are linked to long-duration gamma-ray bursts, GRBs. Without the jets, the explosion would still be impressive, but the concentrated energy in these beams is what turns an already extreme event into the brightest flash in the universe. The physics behind this process is still being unraveled. Some models suggest that the jets are powered mainly by the rotational energy of the central black hole, extracted through the Blandford-Znajek process, where magnetic fields tap into the black hole's spin. Others focus on the role of neutrinos, those ghostly, nearly massless particles, which are produced in staggering numbers during core collapse. In certain scenarios, neutrino-antineutrino annihilation above the poles can help energize the jets. Relativistic jets don't just affect what we see, they influence the explosion itself. As the jets tunnel through the star, they can deposit energy into the surrounding layers, shaping the final blast and contributing to the asymmetry of the debris cloud. This can change how elements are distributed in the ejected material, potentially affecting how much of certain heavy elements get created. In some simulations, without the jets, you wouldn't get a hypernova at all, just a fainter collapse event. On cosmic scales, these jets are also capable of sculpting their environment far beyond the dying star. When they slam into interstellar gas, they create shock waves that heat, compress, and sometimes even strip material from nearby clouds. This interaction can trigger new rounds of star formation, or wipe out regions that might otherwise have formed stars. One of the most fascinating implications is that we might only detect a small fraction of all hypernovae because we only see the full gamma-ray burst if one of the jets is pointed directly at us. If the jets are aimed elsewhere, the hypernova could appear as a less luminous event from our perspective, even though its intrinsic energy is just as enormous. That means there could be many more hypernovae happening than we realize, with most of them hidden in plain sight simply because their jets don't line up with our line of sight. These relativistic jets are a reminder that in the universe, direction matters just as much as raw power. By channeling energy along specific paths, they create events so bright and so fast that they challenge the limits of our instruments and our understanding of astrophysics itself. They are the focused fury of a dying giant, the needlepoint stabs of light that tell us a hypernova has gone off somewhere out there in the dark. When a hypernova's furious display finally winds down, the light fades, the jets sputter out, and the shock waves keep racing through interstellar space, there's still one last chapter in its story, a remnant, small in size compared to the original star, yet possessing a gravitational pull and density beyond anything we can truly imagine. After the chaos, what's left behind is either a neutron star or a black hole. The outcome depends largely on the mass of the star's core after all the nuclear fuel has burned and the outer layers have been ejected. If the core is below about 3 times the mass of our Sun, it can halt its collapse thanks to neutron degeneracy pressure, a quantum mechanical effect that arises when neutrons are packed so tightly that the Pauli exclusion principle refuses to let them be squeezed any closer together. The result is a neutron star, an object only about 20 kilometers across, but with a mass greater than our Sun, and a surface gravity so immense that a teaspoon of its matter would weigh billions of tons on Earth. But in many hypernovae, the core is far heavier than that limit. Neutron degeneracy pressure simply cannot hold it up against gravity's relentless inward crush. When that happens, the collapse doesn't stop, it goes on until the core becomes a singularity, a black hole. The newly formed black hole's event horizon marks the point of no return, beyond which not even light can escape. Surrounding it may still be a superheated accretion disk from the infalling stellar material, continuing to feed the beast for seconds, minutes, or even longer after the initial explosion. Interestingly, in some hypernova scenarios, the black hole actually forms before the jets finish blasting through the star. In these collapsar models, the black hole's intense gravity and spin help power the relativistic jets that define the event's energy signature. In other cases, the jets may be launched during the brief phase when the remnant is still a neutron star, possibly a magnetar, with magnetic fields trillions of times stronger than Earth's, before it collapses further into a black hole once it accretes enough mass. The remnant doesn't just sit there quietly, either. Neutron stars, especially magnetars, can remain active for thousands to millions of years, emitting beams of radiation as pulsars or releasing bursts of high-energy particles. A newly born black hole, while invisible directly, can still make itself known if there's nearby material to consume, lighting up the region with X-rays and even more energetic outbursts. But beyond the immediate aftermath, these remnants are a kind of cosmic seed. A black hole formed from a hypernova might eventually merge with another black hole, sending ripples of gravitational waves across the universe. A neutron star, given the right partner in a binary system, could spiral inward and collide with its companion, creating a kilonova, a whole other kind of extreme event that also forges heavy elements. In this way, the end of a hypernova isn't really an end at all. The compact object left behind becomes part of a larger chain of cosmic events, influencing its surroundings for eons. It is a lasting scar of a star's death, but also a trigger for new astrophysical phenomena that may unfold millions or billions of years later. And perhaps most profoundly, it's a stark reminder of the transformation that a hypernova represents. A star that once bathed its planets in light, now compressed into either a tiny spinning beacon or a silent, lightless abyss. Even after you've gone through the mechanics of a hypernova, the collapse, the jets, the gamma-ray bursts, the heavy element creation, there's still a part of your brain that struggles to truly comprehend the scale. We're used to thinking of big in human terms, the largest skyscraper, the most powerful rocket, the biggest bomb ever detonated. But a hypernova makes all of those achievements look like the flicker of a match next to a raging supernova-scale bonfire, and then makes the bonfire look tiny too. The most powerful nuclear device ever tested on Earth was the Soviet Tsar bomber in 1961, which released about 50 megatons of TNT equivalent. It was so powerful that windows shattered hundreds of kilometers away, and the flash could be seen from over 1,000 kilometers. Impressive, until you compare it to a hypernova. The energy from a hypernova can be on the order of 10 cubed megatons of TNT. That's a 1 followed by 39 zeros, so vast that you can't even reasonably picture it. You'd have to detonate the Tsar bomber every second for longer than the current age of the universe to equal the energy released by a single hypernova. Our Sun, burning steadily for 4.6 billion years, outputs a colossal amount of energy each second, about 3.8 times 10 squared watts. Over its entire 10 billion year lifetime, that's a staggering amount of power. But here's the kicker, a hypernova can release as much energy in a few seconds as our Sun will produce in its entire lifetime. That's the level of fury we're dealing with here. If you scaled human technology to the power of a hypernova, we could boil every ocean on Earth in an instant, melt the crust into magma, and turn the entire planet into vapor before the light from the blast even reached the moon. Yet in the cosmos, this isn't even an outlier, just one possible way a massive star can end its life. The sheer size of the event also humbles our sense of speed and distance. The jets from a hypernova travel at over 99% the speed of light, crossing the distance between the Earth and the Moon in a little over a second. The shockwave and ejected matter plow through interstellar space at thousands of kilometers per second, reshaping regions of a galaxy hundreds of light-years across. By the time that energy has dispersed into the vastness of space, it has altered the composition of countless future stars and worlds. This is why, when astronomers study these explosions, there's a certain reverence in their tone. We can model them, measure them, even predict them in some cases, but we will never control them. A hypernova is the kind of force that reminds you we are tiny creatures on a small rock, briefly aware in the face of something that has no regard for scale as we know it. It's also why they inspire not just scientific curiosity but genuine awe. Looking at the numbers isn't enough. You have to try to wrap your mind around the idea that somewhere, light-years away, an object the size of a star suddenly turned into a cosmic flare so bright it could be seen halfway across the observable universe. You have to imagine the elemental violence of that moment, the unimaginable heat, the ripping apart of matter itself, the blinding surge of radiation, all born in an instant from a dying giant. And then you have to remember, this isn't science fiction. It's happening out there, right now, in the vast dark between galaxies, completely indifferent to whether anyone's watching. The awe isn't just in the scale, it's in the reality. Hypernovae are proof that the universe plays with power levels we can barely conceive, and that what we consider maximum is, on a cosmic scale, laughably small. Somewhere, in the depths of space, A star is reaching the end of its life. For millions of years, it's burned with quiet dignity, forging the lighter elements that make planets and life possible. Around it may orbit worlds that have seen their skies dominated by its brilliance for eons. And then, in a fraction of a second, that light turns violent, transforming from a steady glow into an explosion so fierce it outshines entire galaxies. That is the paradox of a hypernova. It is death on the grandest stage the universe offers, a final act that obliterates the star and everything too close to it. Planets are stripped of atmospheres, life is sterilized across light years, and the space around it is bathed in a flood of radiation more intense than anything our own sun could ever muster. It is destruction so complete that nothing nearby can survive. And yet, it is also creation. In that same moment of obliteration, the blast forges elements heavier than iron, gold, uranium, platinum, stuff that will drift for millions of years before finding a new home inside a forming star, a new planet, or perhaps, one day, the bloodstream of a living creature. The universe recycles itself through violence, and the death of one massive star becomes the raw material for countless futures. It is in this duality that a hypernova becomes more than an astrophysical curiosity. It's a reminder of the constant tension between chaos and order, entropy and structure, destruction and rebirth. Without these cataclysmic events, the universe would be a poorer place. No rich chemistry, no rocky worlds, no life. But with them comes a reminder that creation is never free. It demands an exchange, and in this case, the price is the life of a star far more massive than our own. Standing on Earth, gazing through a telescope, we are impossibly far from these events, yet their fingerprints are in our very bones. The iron in your blood, the calcium in your teeth, the gold in your jewelry, these atoms were once inside stars that died spectacular deaths. A hypernova is simply the most extreme expression of that cosmic truth. So when we speak of them, we're not just talking about distant light shows, we're talking about the very process that made us possible. Somewhere out there, another star is preparing for its own final blaze, and when it comes, the universe will again remind us that it can be both destroyer and creator in the same breath. A hypernova is a cosmic reminder of both creation and destruction on the grandest scale imaginable. A scale so vast that even our most powerful machines can barely record its story, yet so intimate that it flows in the blood of every living thing on this pale blue. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.